Hello and welcome to this first session on atomic structure. So really, I guess this is directed mainly at chemistry. It'll have a bit of a physics feel to it as well. And on this opening slide, really taking something of a historical perspective. And we see some of the big characters who developed the subject of atomic structure in the 20th century. And when you get really stuck into it, it is a very difficult subject when you get into all the quantum mechanics, and I'm actually hoping to avoid that for as long as possible and see that we can make some useful progress using more sort of straightforward and basic old-fashioned physics. But this just gives you a little bit of a quick summary of kind of how the subject developed. So we've got a very young picture of Niels Bohr on the left-hand side, and it was him who really came up with basically the GCSE picture of the atom. So the idea that the electrons are in shells, and this was really Bohr's idea from 1913, and that equation there relates to the hydrogen atom, where N1 and N2 represent the numbers that you give to the shells, and that's giving the energy of a transition between two of those shells. The next guy, Louis de Broglie there, he came up with the idea that electrons can be waves as well as particles, and so that equation there actually gives a formula for the wavelength of a particle, which was a very revolutionary idea at the time. People weren't really prepared to accept it. And the next guy along, Erwin Schrödinger, he thought he could actually show that de Broglie's idea was nonsense by deriving an equation which this wave-particle duality would imply, and that turned out to be his famous Schrödinger equation, which stood the test of time and describes the behaviour of electrons in atoms very well. And so that equation there is on the screen in a very simplified form. And then on the right there is Paul Dirac, the so-called English Einstein. And he really had a theoretical approach which predicted electron spin. So we know electrons can spin up or down. Curiously, Schrödinger's equation doesn't predict the spin of the electron, but the more sophisticated Dirac one does. He sort of incorporated Einstein's work with Schrödinger's work. But as I say, we're not going to get stuck into too many of these really subtle things for a while, and we're going to try and deal with atoms in the most straightforward way we can, and we're going to find some surprising results, how taking what looks like a really kind of naive approach becomes predictively surprisingly accurate. So let's see how that goes. In this second slide, we see two pictures that describe the hydrogen atom electron. We've got the old-fashioned one on the left. This is a bit like the GCSE picture, and the more modern one on the right. This is the wave picture. And the problem with the classical picture on the left is that it's not actually a stable system. So what would happen, according to classical electrodynamics, is that the electron would just spiral in towards the nucleus. And it was this problem that really led to a wave description. So you can see on the diagram on the right there, we have this standing wave model, and as you trace the wave going around the atom, after a full rotation, it joins onto itself. This is a requirement, otherwise it would destructively interfere and destroy itself. And so we have this standing wave around, so the oval there, which represents the circular orbit, that, if you like, is the average position of the electron oscillating in this standing wave form. And so because the old-fashioned form isn't tenable without a wave picture, we tend to just throw it out. I mean, modern physicists just disregard it. But what I'm going to show you now is that actually you can make a surprising amount of progress taking a classical physics approach. And the good thing about it is that it's mathematically very straightforward. When you take the wave picture, you end up having to do some quite sophisticated maths, which is quite hard work. And so I thought best to start off, if you like, with a low-hanging fruit and seeing the surprising progress we can make with the old-fashioned classical picture. And so now here we have this simple approach to hydrogen. So really just making all the assumptions we can. So we're just going to assume the electrons going round and round in a circular orbit. and like anything in a circular orbit, there must be a centripetal force keeping the particle in orbit, and we're going to assume this is the electrostatic force of attraction. So obviously opposite charges attract, and this is described by the Coulomb law. And so on this slide here we've got some of the sort of basic equations of physics, like F equals ma, the formula for the centripetal acceleration there, v squared over r, the velocity of the electron squared over the radius of its orbit. And then here we've got the Coulomb expression underneath that, the electrostatic force there. So E there is the fundamental charge, that would be the charge on a proton, and minus E is the negative charge on the electron. Z there is the proton number, the number of protons in the nucleus, divided by 4 pi epsilon naught, so that's just a constant of proportionality really, the permittivity, and divided by r squared. So curiously, this is an inverse square law, just like gravity. So two masses, obviously the force between them, sort of rather spookily parallel to this, except of course masses always attract, don't they? Whereas with electric charges, they only attract if the charges are opposite, and obviously they repel if it's the same charge. Then a couple of familiar equations, hopefully. After that we've got half mv squared for the kinetic energy, and then the potential energy there in terms of this electrostatic force. And so actually you actually get that potential energy expression by, well, you'd actually integrate the force equation. So effectively, if the electron is infinitely far from the nucleus, we would define that as zero energy. And then if you bring the electron in from infinite distance to a distance r, you see you'd integrate that equation with respect to distance, and then that gives you the potential energy equation there. And so we've got our first little exercise here now. And so we've said that the centripetal force holding the electron into the nucleus is going to be the electrostatic force. And so you can equate those two expressions, rearrange, and get an expression for r. So this is your first little task. What you could do is you could stop this video, have a think about it, and start again. And so in the next slide I'll give the answer. Here we go. So using F equals ma, the centripetal force there is the mass times our expression for the centripetal acceleration, v squared over r, and we're going to put that equal to the electrostatic force, rearrange, and so there's our expression for r in terms of those other quantities. That's our equation 1, we'll be using that again. And now I've got to talk to you about angular momentum. You may have come across angular momentum in physics before. It's a really important property whenever you're looking at electrons in atoms. Mainly I think because it's a conserved quantity, and as the electrons go around the atom they tend to have angular momentum associated with them, and so it's actually a very useful thing to keep track of. So the sort of classical equation for angular momentum, which we give the symbol to L there, that's mv. So mv of course is the formula just for normal linear momentum, and then r will be the distance between, say, the electron and the nucleus in its circular motion. And in fact there's a really important, in fact quite fundamental constant associated with angular momentum. This is the Planck's constant, h, and I've got the value for h there, a really small number. It's got 10 to the minus 34 in it, and curiously the units there are joules times seconds, which you might not have expected given the expression for angular momentum. And so I'm just making the point on this slide that when you look at the dimensions of these properties, if you look at the dimension of the angular momentum in terms of its base quantities, so obviously there's a mass in there, there's a velocity in there, that's distance divided by time, and then there's another distance in there, r, and so using this kind of MLT notation you can get the basic dimensions there of angular momentum. And then the little exercise there at the end is showing that energy times time is dimensionally equivalent to the angular momentum. And actually this relates to a great breakthrough that Niels Bohr made when he was looking at hydrogen, and that's this idea that the angular momentum comes in discrete units. So it's not like a freely varying variable or parameter. It comes in like packets, 1 h bar or 2 h bar. So I should say what h bar is. So h bar there is h divided by 2 pi. And in fact, we're always dividing h by 2 pi when we're looking at angular momentum. And this is because as the electron goes round and round in a circle, let's say, because the circumference of a circle is 2 pi times the radius, 2 pi keeps dropping out of all the calculations, which tend to give answers in radians. And so it's standard to use Planck's constant divided by 2 pi. That kind of gets you into cycles per second. And so h divided by 2 pi is used so often, we just have this abbreviated symbol h with a line across it that we call h bar. And that's what we're going to be using most of the time. So again, you might like to stop this for a second, think about what energy is and what the dimensions are, and show its equivalent to angular momentum. Right, so I've got the answer to the exercise here, and there's several formulae you could use for energy. You could be thinking of work and force times distance. You could think of kinetic energy and half mv squared, gravitational potential energy, mgh. And it doesn't matter which of these formulae you use, when you sort of boil it down to its sort of basic quantities and their dimensions, they all multiply up in the same way. So you'd expect, obviously, they're all energy, so you'd expect them all to be dimensionally equivalent. So it's ml squared t to the minus 2 for all of them. And so when you do energy times time, it then returns to you the same dimensions that we found with the angular momentum. So it just makes that explicit. And so now back to this idea of quantizing the angular momentum. So the angular momentum associated with these electrons, as I say, just comes in these sort of discrete steps. It's not freely varying. And this is the one bit of kind of quantum that we introduce at this stage. This idea that you just have a sort of integer number of units of h bar. And that's what the n is doing in this equation on the page. So we've got the mvr, the angular momentum, is n times h bar. So n will just be an integer, or 1, 2, 3, etc. And so now we've got a couple of equations here. We've got the one on the screen we've just got up here, and there's that earlier one we did where you combine the electrostatic force with the centripetal force and got an expression for R. And it's surprisingly productive if we start combining these equations and seeing what you get. So this first exercise here is to use that expression on this slide, write a formula for R in terms of h bar. So that's fairly trivial, so you just divide by mv, so R would be equal to nh bar divided by mv. And then we're going to combine this with the other equation for R that we did before, equation 1. And so what we can do is we can cancel out the R that way and then rearrange to get an equation for V. That'll be our equation 3. And then we can sort of do things the other way around. So we can go back to our first equation, this time make V squared the subject. We had V squared in the centripetal acceleration formula. And then also taking our equation 2 here from the previous expression, there we are, so we can make V the subject, so that would be dividing by mr, and square that to get V squared, and then we can set the two V squared equations equal to each other, and that way we can eliminate V squared, get an expression for R that doesn't involve V, and that actually turns out to be very useful indeed. And so this equation is going to have a whole bunch of constants in there, plus some dimensionless numbers as well. So n there, that's the just integer number that's counting up the units of angular momentum. So we can think of n as a quantum number actually. That's what quantum numbers are. They're just integers, or they can be half integers sometimes, that just count some quantity which is quantized. Z there is the atomic number, the proton number, so that's just an integer number as well. So if you think about it, in an equation, obviously, either side of the equal sign, the quantities have to be dimensionally the same. So if it's r on the left, that's just a length, the distance from the electron from the nucleus. Then on the right hand side, we can take n squared and z out because they're dimensionless, and all the other constants that are left over, you roll them all together, and they must have the dimension of length. And that length we're going to call A0, the Bohr radius. So again, it's just a constant, it's a whole bunch of constants multiplied together. And in fact, what's really amazing, and again, I just could not believe this when I first discovered it, is again using this sort of simple approach really. There's nothing really fancy about what we've done, just bunged a whole load of constants together. That Bohr radius that comes out is exactly the correct value for the most probable distance of the electron from the nucleus. So, you know, it's normally a very sophisticated calculation to work all this stuff out, and this basic calculation just gets you straight there. So if you like, you could just pause this if you want to work through the algebra and sort of satisfy yourself that it all works. You could pause that and then come back and I'll show you the solution. Here you go. So I've just written out those steps, just equating those different expressions, and then so really the sort of magic expression comes towards the bottom here. So this equation 4 here, this is the equation for the distance r that involves all these constants, loads of constants there, and these two dimensionless quantities involving n and z that we're taking out. There we go. And so that A0, put all those constants into your calculator and it comes out to give you the actual distance of the electron from the nucleus in hydrogen, or at least the most probable distance. Right, so we can actually do some energy calculations using the formulae we've got. So we've got a formula for v squared from our first equation, and we can stick that into half mv squared, the formula for kinetic energy. And what's interesting about that is when you make that substitution, what you're left with looks very similar to the potential energy formula. And so that's what I'm asking you to do in this first question, is to compare the two formulae, how are they related. It's actually a surprisingly significant relationship. Then on to question 2. What have we got here? So here we're going to replace the r by the n squared a naught over z. That's what we established before by combining those equations. And we can also use these constants, which are further down on the page, to stick them into the formulae and find what the kinetic energy is. And I've said the molar kinetic energy, the kinetic energy per mole, because I put Avogadro's number in there. So as chemists, we tend to talk about things per mole. So for example, if you look up the ionization energy of hydrogen in a chemistry data book, you'll get a number in kilojoules per mole. And so using these constants here, they're all in their kind of standard units. So combining all of those, you can work out what the kinetic energy is of the electron, and it's a very surprising result in my opinion. I couldn't believe it when I saw it. And then finally, looking at the kinetic energy and the potential energy, because we find they're related in a very straightforward way in the atom, and then using them to work out the total energy of the hydrogen electron, and then comparing this with the ionization energy. Again, just fascinating result. So again, you can pause this if you like, work through the numbers, and I'll explain give the solution on the next slide. So here we go, here are the answers to those calculations. So when we make the substitution, that v squared expression, into half mv squared, the expression we end up with, as I say, looks very much like the potential energy. It's actually minus a half times the potential energy. So, that is so surprising. I mean, that can't be just a kind of random answer. And in fact, there is a fairly sort of deep connection here. It even goes beyond this sort of electrostatics. So it turns out in physics that any sort of inverse square law that you've got going on gives you this. So for example, I think this also applies to the Earth going around the Sun. So clearly the Earth going around the Sun is a gravitational problem, but gravity is an inverse square effect as well. And so we see the same thing in orbital dynamics of planets. So that's pretty amazing. So it's kind of, yeah, it's ironic in a way that we think the idea of a planet orbiting a sun is a really naive way of thinking about electrons going around atoms when you do chemistry at a higher level, and yet actually this same principle applies just the same to both. And then the next surprising result comes up in question 2, and that is when we collect up all those constants and put them in your calculator, you get exactly the correct answer. You get exactly the experimental value for the kinetic energy. I mean, to 4 significant figures. It just hits it right on the nose. That's just amazing. So we've not used a Schrödinger equation or anything. Just kind of back of the envelope calculation with old-fashioned physics, and we've got the answer. I couldn't believe it. And then on question 3 here, if you say that the total energy is the kinetic energy plus the potential energy, and bearing in mind that the potential energy is -2 times the kinetic energy, it follows then that the total energy is equal to minus the kinetic energy. So we would say the total energy of the electron in the hydrogen atom is minus 1,312 kilojoules per mole. So that might seem a bit strange having a minus value, but it sort of makes sense when you bear in mind that we're defining the zero of energy when the electron is infinitely distant from the proton. And as the electron approaches the proton, it's attracted, obviously, its opposite charges attract. And so if you want to get the electron back off the atom and back out to infinity, you've got to put energy in to get the electron back up to energy zero. So that kind of explains why you call the energy a negative value in atoms. So yeah, most of the time we call the energy of electrons in atoms negative energies. But do beware, sometimes people look at it from the other point of view. Sometimes, a spectroscopist might say, well, let's call the energy in its ground state zero. So you just need to keep your eye out. Sometimes they'll define the ground state as zero. But I think in our calculations, we'll be taking zero to be what you'd call the ionization limit, when the electron is free from the atom. Now, I can't resist telling you about atomic units. These are amazing things. I remember when I first met atomic units, I just couldn't believe it was true. It's amazing. You just take the fundamental constants and you set them all to 1. So you take the fundamental electric charge to be 1, the mass of the electron to be 1, h bar to be 1, h bar also known as the reduced Planck's constant, and 4 pi epsilon 0 to be 1, which you see in the potential energy expression. And it's so convenient because it means you can just start doing calculations in your head. You don't need a calculator at all, just multiplying by 1, dividing by 1. And also those constants there, they all take the value of extremely small numbers, so it's quite cumbersome doing calculations with them. So you've got to be a bit careful. You've got to be, got to keep your wits about you. It's okay if you're comparing like with like, but obviously on slightly thin ice moving between different quantities. Now, in terms of energy, these atomic units are given the name Hartree, abbreviated to HA. And there's some exercises here which just illustrate the simplicity of the atomic units, working out the values of certain quantities in atomic units. And so these quantities which you've met before, these are all just basically products of fundamental constants. And so not surprisingly, they tend to turn out as 1, looking at these rules. But actually one of these is not going to be equal to 1. And if you look at those, it's going to be the total energy of the hydrogen atom electron, isn't it? Because you remember we said that you see with a 4 pi epsilon 0 being equal to 1, this means that when you work out the potential energy of the hydrogen atom electron, that's going to come out as -1 Hartrees. But of course the total energy of the electron is the potential energy plus the kinetic. And we know that the kinetic energy is equal to minus half the potential energy. And so therefore the total energy of the electron comes out to be minus the kinetic energy of the electron. So you just need to bear in mind there's going to be an important factor half in there. Anyway, have a think about those exercises and I'll give you the answers in a second. So here are the answers to that exercise. And so yes, when we look at the total energy of the electron there, you can see in that formula we've got a half in front of it, so it's minus half times half the potential energy there, and so it turns out then that the total energy of the electron is minus half a Hartree in the case of hydrogen. But yeah, it's quite fun this, so you can kind of start doing calculations on a sort of scrap of paper rather than having to write out lines and lines of big numbers and small numbers.